Welcome back, Algorithm here. Today we'll be solving Unique Paths 2, LeetCode 63. So, this question is very simple actually. I think it's much better to explain this through a diagram than to actually read out all the description. So, you're the robot and you have to get to the right bottom corner. That's the star right here. And the robot can only move either down or right at any point in time. And we are also given an obstacle, as shown in the diagram in the middle of the grid, and the robot cannot go towards this square. So our job is to calculate the number of possible unique paths that the robot can take to reach the bottom right corner. So if you look at the given example, the answer is 2, because the robot can go here, and then it can't go down, so it'll go right, and then it can't go anywhere else other than downwards. So it goes down once and twice, and that's the first path. And then the second path is like such. So as you can see, this can be a bit overwhelming, but it's typically when there is a grid in the example or the description, it's a good indicator that the question will be either backtracking or dynamic programming. This question happens to be dynamic programming's question, and if you don't know what dynamic programming question is, I highly recommend that you read or watch a video on it, and once you know it, it becomes very simple. The hardest part is recognizing which parts of the problem we will be using as dynamic programming. So, for this question, there's two parts that we have to figure out. The first is how are we going to calculate each cell? And number two is what are we going to do with the obstacle cells, right? So if this is the goal, let's say, how many ways can we reach the goal when we're here? We can reach exactly one, right? How many path can we make when we're here? Only one, right? Because we can just go right once, right? Then how many paths are there if the question was here? So like such. If you're here, you can only go one way, right? How many paths are there when you're here? You can't go right, so you can only go bottom, so you're one. Now, how many paths are there when you're in this middle? Assuming this is not the example that we're looking at. Well, you can go right once and then down once, right? And then you can go down and then right, which has unique two paths, right? At this point, you should recognize what it did with its previous cells. So we looked at how many paths there are in this cell, and we looked at how many paths there are in the bottom cell, and we added that up, right? Typically, the relationship is not as simple as the one that we have today, but it's how you would approach these kind of problems where for the first few cells, you'll be able to solve it in your head yourself. And then afterwards, you have to find a pattern, and you typically want to look at which part of the problem that you had to look and what kind of relationship there is. It's not always straightforward, but I think it comes with practice. So if you look at here for this cell, there's again two possible options, going down or going to the right. So there's three paths in total here. If you don't believe me, you go down once and to the right, right? And then for here, you can go like this, or you can go like this, right? So that's three in total. So what about here? There's only one path. For here, there's three, right? You can go here and then down, or you can go here and then like this, or like that, right? Here it's 6 because you can go once and then 1, 2, 3, or you can go down 4, 5, 6, right? Let's just cover the edge cases for now. How would we calculate if we're here or here or here or here? We noticed that it's out of bounds, so we just return 0. We act as if there's 0 here, and for these ones, the bottoms are out of bounds, right? So we just pretend like it's 0. And for the goal gave 1 here, right? And that's how we were able to solve the question. Now, let's try to solve this question when there is an obstacle, right? Again, to figure out the relationship, just try to solve first couple of cells and you'll pick up the relationship quite simply. So the obstacle is right here. I'll just put an X here for now because we don't know what the relationship will look like. But the destination is here. So we'll put 1 here and then we'll start again. So it'll be 1 here and then 1 here. And we act like there's 0 here, right? Here again, 1 here. For here, we don't know, so let's skip it. For here, if you look at it, we can only go down and then go, right? So this to me suggests that we treat this almost like if it's as if it's 0. That's my theory for now, but let's continue and see if that's correct. For here, there's only one way. For here, there's also only one way, right? So it looks like my theory is correct. So let's look at here. There's 2, right? You can go here and here, which is the answer we had before, right? So we'll try to code this up. So first, we'll get the dimensions of the grid. So y equals length of obstacle grid. Here we go. And then x is the first element because it's a grid. Every element will have same length. So usually the way I solve dynamic programming would be to make a new array called dp and then fill it in with corresponding numbers, but we're actually given the grid, so I wanted to save some memory space. So what I'm going to do is actually utilize the obstacle grid that's given to me. So I'll just iterate through the grid and modify the values accordingly. Now, it's important to note that in an interview, your interviewer might not like this and might count this as memory space. So talk to your interviewer about this and make sure what they're okay with and what they're not okay with. So I'll first check if the obstacle grid of the current iteration is 1. That means that it's an obstacle. So I'll just always set it as 0 if, and I want to check if it's the first iteration in the given loop, meaning that it's like the bottom right. If it's that, we would set it as 1, right? So else if obstacle grid, else if y equals y minus 1 and x equals capital X minus 1, then we set the grid to be 1. Now I'll do the ones that are within the bounds first. So y plus 1 is y and x plus 1 is x. So both the y and x value are inbound. We set the current value to be the one underneath it and the one beside it. And then if this is not the case, one or both dimensions are out of bounds. So what we do is new y new x equals 0, and then if y plus y, if y is in bound, we would set new y to be obstacle grid y plus 1, and if x plus 1 is within bound, we would set new x to be, and then just set the current grid to be y, the new yx plus the new y. And we return the first grid, which is 0, 0, and that's actually it. Let me just double check if I have any typos. Oh, there's a typo here. It has to be equals 0, not comparison. Whoops. And here too. Wow, I don't know what I was thinking there. Other than that, everything looks good. Now let's pass. As you see, I passed with flying colors. Now, the time complexity is obviously big O of m times n, where m is the grid. Space complexity is O of 1, or depending on the interviewer. That's it. Thanks for watching. Please like and subscribe. And if you have any questions that you would like me to solve, let me know. See you tomorrow.